Okay, any questions about anything? Okay, can any of you hear there's just some hammering, for example? I don't know if you can hear it or not. It's definitely pretty audible for me if I take off the headset. Chat. Okay, so so far it's quiet, I guess. Okay, well then, I can always relocate in the middle of the hour if it gets to be too distracting. So let me know. Okay, so then to resume what we were discussing. Okay, so so we're studying this equation with where the domain D is a half space and B is the distance from the z-axis. Okay, and so we've derived, for example, equivalence of the Biot-Savart law on this domain. So this expresses the velocity in terms of the vorticity. And we've also derived an expression for the stream function psi, which is useful because the energy of the system, so the conserved energy is here. There's a factor of pi because that's the right factor to correspond to the 1/2 the L2 norm in all of R3 for the corresponding three-dimensional flow. Okay, so this we can express the energy in terms of psi. And so we're in the middle of a lemma, which so here is just repeating this definition: the energy of a vorticity distribution omega is given by this thing here. So we'd started proving a lemma which says the following. So we assume we have a vorticity distribution who satisfies these assumptions. And I like these assumptions because these are all things who are preserved by the axisymmetric order without swirl evolution. Let's see, there's a, okay, good. So, so these are all preserved by the evolution. So we assume, and so what I have in mind, remember, is that the vorticity should look like a small blob at distance r equals 1 from the z-axis, and maybe supported in a ball of radius order epsilon, if I like. And so these assumptions are consistent with that. And indeed, we can check that one can write down initial data. If I chose initial data to be the characteristic function of a ball multiplied by the right number, 1 over pi epsilon squared. And if I can find some, you see, if I do that, if I take a ball, I take omega to be 1 over pi epsilon squared times the characteristic ball of radius epsilon, then this will hold for sure, the first condition. And that will equal 1. And the second condition will be, well, it'll be, if the ball is centered at a distance r from the origin, then it's supported between r minus epsilon and r plus epsilon. And so I can see that the second integral will be the center of the support up to errors of order epsilon. And so by the intermediate value theorem, I can see that there's some radius near 1 where I can exactly satisfy this condition. Okay, so it's so the kind of data I've just described will satisfy these conditions, and I have in mind applying this to solutions of the axisymmetric order with this order. Okay, and so the conclusion is that if And so again, the underlying idea is that the first three assumptions we asserted that the energy is maximized under these assumptions, and in fact the maximum is of order 1/2 log epsilon plus a constant. And so what this is saying is that if the energy is close to maximal, then this implies certain conditions on the sort of structural information on the vorticity. Okay, and the information says the vorticity is quite concentrated around some point x star. So it's quite concentrated around a point x star, and the r coordinate of x star is close to 1. We just started rewriting the energy. And so the energy is the integral of this thing up to a constant multiple of pi. And so, okay, so all we did was we messed around with the integral who defines this g, and found that we can rewrite this in this way, where S is the ratio of the distance. So here, X and X prime are the points R, Z, and R prime, Z prime in the half plane. So S is this ratio, X minus X prime squared over R prime. And so the leading term we found is here. And then I began to rewrite this. And so I can bound this above by this. And then I rewrite that. And so now I'd like to continue. And so then, now if B is between 0 and 1, then let's say this is this well, then I can say this is bounded below by, or bounded above by 1 plus 4r prime. Right, 1 over b squared is bigger than 1 over b. And this is log of 1 over b plus 1/2 log this. And this in turn is less than this plus, say, 2r prime. So 1 log of 1 plus a is less than a for a positive. It's also for a negative. Okay, good. And so, so then we can say that so the energy, remember my goal was to rewrite this energy in a more, my initial goal was to rewrite the energy in a more usable form. And so the energy is just the integral of pi times this quantity. And so let's see. Okay, and so the pi will cancel this. And then I believe I'll have, let's copy it down from someplace. Okay, so I integrate over the half space twice. And I'll have a square root of r prime coming from here. And then we have, say, log 2 plus 2r prime plus log 1 over b. And then let's just, let's throw out the contributions from where b is bigger than 1. Okay, so those will be right, this is always, I believe this is right. Okay, and I might need the characteristic function to multiply everything. I don't, it doesn't matter much. So you let me know if that hammering is bothering you. These are noise canceling headphones in principle. So, okay, so then I'd like to get rid of these terms. And so note that, what do we have? So I have a and I forgot the most important thing, or an important thing. Okay, so I have to multiply by the vorticities. Okay, and so I have a term involving the square root of RR prime times log 2 times the omega times omega of x prime. And I have a term involving RR prime to the 1/2 times RR prime. So these are RR prime. Well, okay. Let's do an easy estimate. 1 plus R squared, R prime squared. The same is true for R prime to the 3/2. Okay, so here I would have the first one, I would say, for example, 1 plus RR prime, 1/2 plus 1/2 RR prime, I could square it again. And so I would get these by Young's inequality with some constants who I haven't bothered to keep track of. Okay, so for example, this is bounded by some constant times 1 omega of x prime plus another constant times the integral. And let me write it this way. R squared omega of x dx times R prime squared omega of x prime dx prime. Okay, and then these are, so remember we assumed that the these quantities here are equal to 1, in fact, are bounded. And so, okay, and so this whole thing is less than c is bounded by some constant who we could compute in principle. And remember, the constants may change from line to line, but we could always compute them in principle if we wish to, or at least estimate them. Okay, and so then, and so I'm left with the energy of omega is really the only surviving term is this one. And remember, b is the distance from x to x prime. And so I like this because it looks like the energy I'm used to a little bit, except for it looks like the energy on R2. Okay, and so my conclusion is that the energy of omega is bounded by, let's call it E1 of omega, and then all the other terms are constants. I guess it's 1/2 the integral over the half plane twice of R prime to the 1/2, and then you know what? I think to be safe, I think I should do this. Anyway, what I'm left with is log of 1 over b times the characteristic function of, so I'm looking at that where b is between 0 and 1. And so I can write that as that's the positive part of the log. And let's write what b is. Okay, good. And so I've taken my initial assumed lower bound on this funny energy, and I've deduced from it a lower bound on energy who is more recognizably, who seems like it may be easier to work with. Okay, so then here's my next goal. And so what's going on in the background is that, in fact, all these bounds I attain are pretty close to sharp. At least the leading order term is sort of sharp. And so let's call this star. Okay, so this is equation star. Okay, and now I want to define and so the okay, so informally the idea is that somehow these normalizations on the center of that the integral of omega and the integral of omega r squared are both equal to 1. These will force the mass to be concentrated around r equals 1, the force is to be concentrated around r equals 1. And so we can sort of think of these terms as being 1. And then the energy is like 1/2, is like a, let's, let me rewrite this. Okay, and so the constants here are different, but in every case. Okay, let's make it C prime. Okay, and so this E1 energy is bigger than log epsilon, 1/2 log epsilon, up to a constant factor who we'll kind of ignore. And so what this says is that this we have total vorticity 1, and so it better be concentrated on the set where x minus x prime is less than epsilon, because if I want to get something of order log 1 of epsilon out of this. Okay, so and so anyway, that's the hope. And so what I want to do is, well, okay, let's just write it down. So next we'll define what is it, m tilde. So it's just the part of this, let's see. So if I omit the log from the integrand, let me call that m tilde. And okay, note that, as we said already, well, in fact, I'll do something a bit more precise than what I did before. So if I want, I can say 1/2 plus r prime over 2, and this is less than 1/2 plus 1/4 r squared plus r prime squared. So so m tilde here. Oops. M tilde is bounded by 1/2 plus 1/4 r squared plus r prime squared. And then I integrate. And this is equal to 1 because the integral omega is 1. the integral of omega of x is 1, the integral of omega of x prime is the same. And so every time I integrate, I get 1. Okay, and so what I'd like to show is that, in fact, that I'd like a lower bound for this m tilde to show that, in fact, the m tilde is close to 1. And so the upper bound I've proved is almost saturated. And so the general idea in arguments of the sort is that whenever you have an upper bound who's close to being saturated, then good things happen. And so then, in other words, for example, if m tilde is close to 1, then that will say we're close in every case to the equality case for these inequalities, and that will give us information. Okay, so let's rewrite star. And so what do I want to do? I'd like to say, I'll do it like this. Okay, and this is bigger than looks like log epsilon over 2 times 1 minus m tilde plus whatever I had up here, a constant, c. Okay, and then the right-hand side is the square root of r prime times log epsilon over 2 plus log positive part of 1 over x minus x prime omega dx prime. Okay, so epsilon is less than 1, so absolute value of log epsilon is the same as minus log epsilon. Okay, and so this is star rewritten, and I'd like to, so you remember a while ago we had a kind of a vorticity concentration inequality, and well, we did what we're about to do there. So well, the point is I can rewrite this as sorry, the half is wrong. I think that's what I want. And good. And so I can rewrite this as log of epsilon over x minus x prime if, or times as long as x minus x prime is less than 1. Okay, and so for any positive r, then let me integrate over the ball of radius r times epsilon, and for any x in the half space, if I integrate over the ball of radius r times epsilon of x, this integrand, okay, and so let's see. Let's assume that r is less than 1 over epsilon. So then I'm satisfying this condition. Okay, and so the point is that the integrand is negative if x minus x prime is bigger than epsilon. And so this is, if I write this as the integral over the ball of radius epsilon of x of the same thing, it only gets bigger. And then okay, so here's what I'd like to do. So note r prime is less than r plus epsilon in the ball of radius epsilon around x, where x is r z for, and so for this is for if x prime is here. And what else? And so, and that's right, and say omega of x prime is less than lambda over epsilon squared. I think I want only a, I think here I want only this. So the integral then is bounded by lambda times r plus epsilon times, let's see, sorry. So the our assumption was that vorticity divided by the radius r is bounded by lambda over epsilon squared. And so, and this is r prime, and then this is less than. So omega of x is less than lambda times, again, r plus epsilon over epsilon squared x prime, if x prime is in the ball of radius epsilon around x, okay? It's because, again, r prime is at most r plus epsilon. Okay, and so then I, so if I then replace, say, this and that, we find that okay, so the integral, the above integral, and so we should have then lambda and r plus epsilon squared over epsilon squared, and then the integral of the ball radius epsilon of log of epsilon over x minus x prime dx. So I've gotten rid of the omega and I've replaced by x. And then this, you can do the integral explicitly and you get lambda r plus epsilon squared, and let's say it's probably pi over 2. So there's epsilon squared who cancels the factor 1 over epsilon squared. Okay, and this was the, if you remember, there was we had a kind of an inequality like this a while ago, and this was the core of the earlier estimate also, of this earlier vorticity concentration estimate that we proved a few weeks ago. Okay, and so then, okay, so what have we said? We've said that the integral near any point, we have an upper bound on the integral near any point, x. And so, and we also have a lower bound on, right, so we have a, we've just proved an upper bound for the part of this integral of, say, the inner integral concentrated near a point x, And then we also have a lower bound. And so what's the conclusion? So, okay, so what I want to do then is integrate the above multiplied by omega of x dx. And so that gives me a upper bound on the integral of over, so we have then and so then let's subtract from say the rewritten. So we rewrote inequality star in this form. And this says that the integral over all of R2 is bounded below. The integral over this near the diagonal is bounded above. So by subtraction, we find that the integral over the set of points x and x prime such that x minus x prime, so I'm far from the diagonal of this r prime. That this is bigger than, say, log epsilon over 2 times. So this just, I'm just recopying the old downhill side of this inequality. But I have new stuff here from these terms. Okay, and so I guess I should have said okay, when I did this integral here, I'll get more integrals involving r squared omega prime and 1 times omega prime, and those again are controlled by the assumptions on the bounds of the integral of r squared and the integral of 1. Okay, and so that gives rise to new terms here. On the, and I think I have a minus sign here, probably. Okay, so now let's stare at this. And so the point is, so the left-hand side is definitely negative if r is 1, for example. Right, because then log of 1 over x minus x prime is always means so then this quantity parentheses is always negative. And so by taking r equals 1, we conclude that 0 is bigger than the right-hand side, which gives me a good lower bound for this m tilde. If I rewrite that, I'll find that I divide by log epsilon over 2, and then I'll find that m tilde is bigger than 1 minus a constant times 1 plus lambda over log epsilon absolute value. Okay, so this is good. And so we know that this m tilde is less than or equal to 1. That was a sort of a trivial upper bound. And then using this structural information that comes from the assumed energy lower bound, we're able to show that in fact m tilde is close to 1. And so that all the inequalities that we used in proving that m tilde was less than or equal to 1 are in fact almost sharp. almost saturated. Oops. Okay, so then what's next? So this is the what I was aiming for with the recent arguments. And so then, okay, so now write let's say f of r and r prime. So this is the, well, I'll write it out. And so this is the so the inequality I used before in proving in deriving the upper bound on m tilde, which is the inequality that says that f is non-negative. We can see that f is non-negative because it's exactly, what is it? It's 1 minus r prime squared plus 1/4 r minus r prime squared. Okay, and so the point is that these omegas have to be concentrated. Omega and omega prime have to be concentrated on the set where f is close to 0, where this inequality is almost saturated. Okay, and so then it's immediate that let's write it out then see why it's immediate. Okay, that's clear. If I add square root of r prime to both sides and multiply by 2, I get this inequality. And one can check that what 1 minus r squared well, okay, it's really f of r prime for all x and x prime, both in the half space, such that f of r prime is less than 1. Okay, without writing out the details, let's see how do we do this. So I can see that if this is, say, so r and r prime are both positive, say this is r prime. If f is less than 1, that means that r minus r prime is so we're close to the set where r is equal to r prime. And we're close to the set where r prime is equal to 1 because of this, which is here. And so we're in the, I don't know, the intersection of these things in some region like this. Okay, so it's a compact set. Anyway, the set where f is less than equal to 1 is compact. And so then it suffices to check that, well, okay, so what could go wrong with this inequality? All I have to worry about is where f vanishes. If I can show that this inequality holds in a neighborhood set where f vanishes. So f is that 1 minus r squared over f is strictly positive in neighborhood at that point of there. Then I can say it's positive everywhere in this compact set by just compactness. Okay, and so to show that this is so the idea is that, well, d squared f dr squared is bigger than 0 at here. So so near to the only point where it vanishes, it grows quadratically. And so we have this inequality near there, and then there's false by compactness. Okay, good. And so then I want to use these two inequalities. And so so I'm going to rewrite what I had before in terms of f. And so we'll write f of r prime, omega of x, omega of x prime. So I'm just messing around to take advantage of what I know, which is that this that we have almost inequality. So this is 1/2 plus 1/4 r squared plus r prime squared minus the square root of r prime omega of x prime. And this is, I have an inequality here for some reason. I sort of think the first one is a, oh right, yeah. So again, we're estimating this integral by 1. That's the upper bound. Okay, and then the other term is really m tilde. Okay, and then also this is let's see. And also okay, I have to combine some things. So what I want to do is I want to look at this double star, I think I called it. Right. Or where was, what am I looking at? I guess I'm looking at this inequality. Which we can call triple star. Okay, and so I'd like to deduce things about this from knowing that you know, from these considerations we're considering below. Okay, and so then right, and so first of all, I claim that the right-hand side is, well, the point is that m tilde is at most 1. And so this is bigger than minus c times 1 plus lambda. Okay, that's the first observation. And then also, this is less than minus log r in the integrand. And so, and the point is that this is log of epsilon over x minus x prime, or it's minus log of x minus x prime over epsilon. And so in integrand. Okay, and so my conclusion then is that the integral of this thing times log r with a minus sign is bounded below by this stuff. I can then multiply everything by -1, and I will find that, and then divide both sides by log r, and I will find that the, so by messing around, so by algebra, using the above, triple star, we find that 1/2. So this is just, well, okay. Prime, omega of x prime is less than, and so this is just by the sequence of algebraic operations I described. Okay, and so what do we have? We have this upper bound for f plus, for f times omega prime, an upper bound like this. And we have this upper bound. And let me see. Let me do this. We've said that r is less than 1 over epsilon. And so log r is, so 1 over log r is bigger than 1 over log epsilon. Okay, and so what I'd like to do is then take a linear combination of these two to add this and use the fact that well, okay, so let's write it down. So a linear combination of the above implies that the integral over the double half plane of the characteristic function of x minus x prime bigger than r epsilon times plus c f of r prime I'm copying my notes and I feel like I'm missing a square root of r prime here. Okay, so we're almost at the end of the proof. And right, so I want to use the fact that okay, sorry, we're doing this. So I add to f a multiple of the square root of r prime, and that gives me that gives me 1. And then I take still more of f. And in that way, I get a factor of 1 here with the RR prime taken care of, absorbed into this inequality. And I have some of f left over. Okay, and so then, and this is multiplied by omega of x prime dx prime. Okay, and so then the point is that since the integral of omega is 1, there exists some x such that this integral is less than, so the integral with respect to omega prime is bounded by, so the integral over the half space of the same integrand is bounded by the same right-hand side. And then, so now I think we've done what we wanted to. So what we've shown is that the amount of vorticity outside of a ball of radius epsilon around x is small. And we've also shown that the integral of, we've shown the integral of this is small, and that implies that by this inequality that the integral of 1 minus r squared is small, and hence r is small also. And so, or rather r is close to 1. And so by getting an upper bound for this quantity, we get an upper bound for that quantity. Okay, so this went over. I realized I was just sort of messing around with technical details. I'll see next time if I can summarize this in a way that makes it more comprehensible. But anyway, we can see at least this is a very useful result for what we're going to do. And sorry to get kind of lost in the weeds. I'll see if I can sort of clarify the ideas in as much as there are any next time. Okay, let me stop the sharing.